first, we just have a couple definitions, some things that we want to talk about. We know if something is a function, that means x doesn't repeat, it passes the vertical line test. If something is one-to-one, if you have two different inputs in the domain, you get two different outputs in the range. Another way to say this is y never repeats.
Can I go to the bathroom?
Yes. I wasn't expecting you guys back. Okay, so if it's a function, x doesn't repeat. If it's one-to-one, your y does not repeat either. So first, let's look at a couple and decide if they're one-to-one. So this is my function, these are my x's and my y's. Is this one-to-one? No. Why? Okay. Is b one-to-one? Yes. None of the y values repeat. A lot of times the shorthand I put is I just say 1-1 to stand for one-to-one. Okay, to decide if something is one-to-one from the equation, it's actually a little bit more work. When we were trying to decide if equations were functions or not, we were basically looking to see if the x would repeat. If it's one-to-one, the y can't repeat. So what we do is assume that two y values are the same. F of a equals f of b. The only way we can get the same y value if it's one-to-one is if I plugged in the same number for x both times. So we'll start out assuming f of a equals f of b. Two y values are the same. And then we'll solve that. If we get that a equals b at the end, it is one-to-one. If we get anything else, it is not one-to-one. So for instance, if I looked at this one, okay, the algebraic way to decide if they are one-to-one is saying f of a equals f of b. F of a says you go to your equation, you replace your x with an a. F of b says we go to our equation, we replace the x with a b. Now I'm just going to solve for a. So if I want my a by itself, I can subtract my 7. Divide by -3. And I get a equals b. So is this one-to-one? Yes. I found that the only way that I could get the same y value out was if I put in the same x's to start with. So if I look at b, if I do f of a equals f of b. So f of a, we go to our equation, we plug in an a for the x. F of b, we're putting in a b for the x. If I asked you to solve this for a, what would you do? Square and the square root cancel each other. Then what do we do? So I have negative a squared equals negative b squared. Divide by -1, so a squared equals b squared. How do we get rid of a square? When you add a square root, what else do you have to have? So I get that a could be a positive or a negative b. So they could be the same, or they could be opposites. I'll get the same y value if I plug in +3 and -3. So is this one-to-one? No. Can you tell me what part of this function made it not one-to-one? The square. Because I had to add a square root to get rid of it, and that put a plus or minus. So when something has a square in it, it's not going to be one-to-one. All right, if we're looking at a graph, we can tell another way. We know looking at a graph, you can tell if something's a function by checking if it passes what? The vertical line test, because x can't repeat. So looking at a graph, if y doesn't repeat, it has to pass the horizontal line test. So if you can draw a horizontal line that hits it more than once, it is not one-to-one. If it only touches once, it is. So for instance, if I gave you something like this, is that one-to-one? No, because I can draw a horizontal line that hits this graph several times. If I gave you something like this, is that one-to-one? Yeah, it has lots of little curves in it, but it never failed the horizontal line test, so that one is one-to-one. All right, so using what you know about graphs, sketch the graph of each of these and tell me if it's one-to-one or not. So what's x squared look like? Parabola. And we've already said that's a problem, but now we see it from the graphing standpoint. A parabola is going to fail the horizontal line test every time. So that is not one-to-one. What's x cubed look like? So is that one-to-one? Yes, that one is one-to-one. No matter where you draw a horizontal line, it only touches once. Okay. Do you guys feel like you can decide if something is one-to-one by either looking at the graph or doing the algebraic method? All right. If things are one-to-one, then we can find their inverse. The inverse is like the opposite of something. If I take a number and I add 2, what would be the inverse, the opposite of adding 2? Subtracting 2. Okay, if I take a number and divide by 4, what's the inverse? Multiply by 4. So it's finding the opposite. What it does is it flips our x and y values. So if a function is one-to-one, we can find its inverse by flipping all the x and y values. The symbol for inverse is f to the -1. That does not mean 1 over in this case. It is just a notation to stand for inverse. So we'll start with just looking at some ordered pairs, and then we'll carry this into equations. If I said this was my function, this set of ordered pairs, can you tell me what the inverse would be? What points would be in the inverse? You don't want to change the sign, you just literally flip them. So the first order pair was -3, -27. So if I flip them, it's, okay, I had the point -2, -8, so that becomes -1, -1. When I flip it, doesn't change. 0, 0 when we flip doesn't change. 1, 1 doesn't change. 2, 8 would become, and 3, 27. So it doesn't change the signs, it just flips x and y. So on B, tell me the points in the inverse. The reason we said it had to be one-to-one in order to find the inverse, if it wasn't, if one of the y's got repeated, so for instance, let's pretend this point was -3, -5. So it would not be 1 to 1, correct? When I reverse those points, what's wrong with this? It's not a function. So if it's not 1 to 1, the inverse will not be a function. So that's why we only find inverses if it's 1 to 1 to begin with, because we're only talking about functions right now. Your shoes are in the office.
Yeah, I just went.
Okay. So, a couple things to note. The domain of the original function, those were the x's, it became the range in the inverse. X and y flipped roles. The range of the original became the domain in the inverse. And I think I did give you this notes handout.
I already did it.
Okay,
found
you
it
found the old
last
one?
year. Yeah.
Perfect. Okay, another thing to note, inverses, like we already said, are the opposite, right? I said if you take a number and you add 2 and subtract 2, those are inverses. Okay, if my number is 5, and then I add 2 to it, what do I get? 7. Then if I do 7 and I subtract 2, I'm back to 5, what I started with. So if you do both the inverse and the actual function, they cancel each other out, and you're just getting your original value back. So if I ever ask you to decide if 2 things are inverses, what we can do is check their compositions. We can see, do they cancel each other? We need to check F composed with G and G composed with F. In order for them to be inverses, both of these things have to equal just x. They have to cancel one another out. If either one doesn't work, then that means my functions are not inverses. So when I do f composed with g, that means f of x cubed. Okay, if I put that into f, so the cube root, I'm replacing my x with an x cubed. The cube root of x cubed, what happens? Those cancel and we get x, which is what we wanted. If they're truly inverses, they cancel each other out, and we get what we started with. So we check the other one, g composed with f. So f is the cube root of x. If I put that into g, g is whatever we put in cubed. So if I take a cube root cubed, they cancel each other, and we get x. Since both of them equal x, they are inverses. If one didn't work out, we would not have to check the other one. We could just stop and say they are not inverses. Let's try a couple more of these. We'll do some with a little more to them. So f is 1 over x minus 1. G is 1 over x with a minus 1 on the end. So if I want to see if they're inverses, we can do f composed with g. So g is 1 over x with a minus 1 on the end. If I put that into f, f is 1 over the thing I'm plugging in minus 1. Are you guys with me here? So I'm replacing my x right now with this 1 over x minus 1. We get 1 over x minus 2. Is this the same thing as x? No. Is there anything I'm going to do to turn this into x? No. So what do I say right now? Not inverses. We don't even have to solve any further. Okay, you guys try the next one. Decide if these are inverses. So, f composed with g. That would be f of the 1/3 times x minus 4. If I put that into f, f is 3 times whatever we put in for x plus 4. So if I put in my 1/3 times x minus 4. 3 times 1/3 cancels, so we have x minus 4 plus 4, which is x. So far so good. You do have to check the other one because it is possible for one of them to equal x and the other not. So we have g of 3x plus 4. So g is 1/3 times the thing we plug in minus 4. So minus 4 and plus 4 cancel, so we get 1/3 times 3x, which is x. So both ways turned out to be x, and they are inverses. Any questions there? Angela, I do have that. Okay. In terms of talking about the graphs, we know that inverses just flip the x and y. So that makes a function and its inverse symmetric across the line y equals x. Okay, because x and y are just reversed. So we can use that a couple different ways. If we have the graph of a function, we can flip all the x's and y's in its ordered pairs to graph the inverse. We could also just try to draw a mirror image. I think for looking at a graph, it's probably easier just to do points for most of us. So let's practice trying to draw this one. So if I wanted to graph the inverse of this line, let's start off, we know how to graph lines. So we'll just graph that line to begin with. So 3x minus 2, that's a line y-intercept of -2, slope 3, so up 3 and over 1. So that's my original. If I wanted the inverse, I could think about these points. This is the ordered pair, 0, -2. So what would the point be on my inverse? Okay. This is the point 1, 1. What will that point be on the inverse? Still 1, 1. My lines are not perfectly straight, but use your imagination. Pretend they are. So if you graph the line y equals x, that's a line with a y-intercept of 0, slope of 1, it goes right through the middle. So we should be able to see that it is a mirror image across that. If we fold it on that line of symmetry, y equals x, they reflect. But like I said, in general, I think it's easier just to look at ordered pairs and reverse x and y. So let's graph one more. So here's a graph. I want the inverse. So we're just going to take some points. This is the point 1, 2. So where would that go? 2, 1. Here's the point 0, 1. So that would go to 0. -1, 0. We'll go to 0, -1. There's that. -2, -2 would stay at -2, -2. So our inverse would look like that. Any questions so far? Okay. We're almost done. I'm sorry. Thank you guys for bearing with me, letting me teach for a whole class period today. So the last thing we want to talk about is how to actually find inverses. So we know that inverses switch x and y. So that's ultimately what we're going to do. We're going to switch x and y. first of all, we need to make sure there's both an x and a y in our equation. So most of them are going to be written in function notation. So the first thing we're going to do is replace that f of x with a y. We know f of x and y are the same thing. We're going to change it to a y. So that then we can switch x and y. So our y becomes an x, any x becomes a y. Then we want to put it back in function notation. So then we will solve for the y and change it to f inverse, just to show that we have found the inverse at the end. So let's do some of these. Start off with the next one. So f of x is the same thing as what variable? Y. So first step, instead of f of x, we write a y. Okay, next step. What do inverses do? Okay, so my y becomes an x, my x becomes a y. Now we want to write this in function notation. So we will subtract over the 3, divide by 2. And final step, to show that we found the inverse, instead of y, what are we going to write? That f to the negative 1 means f inverse of x. Any questions on that? Let's do this one. We're also going to do domain and range on this one. So first step. Instead of f of x, we write y. Okay. Then, inverses switch x and y. So instead of y, we write x. Both of these x's become y's. I want to solve for y now. What should I do first? Okay. So if we distribute, we get xy minus x equals 2y plus 1. I'm trying to solve for y. I have y in 2 different spots. So I need everything with a y on one side. So I'm going to subtract over this 2y. And everything without it on the other side. So I'll add my x over. So I reordered it. Both terms on the left have a y. Terms on the right do not. They aren't like terms, so I can't actually combine them. How does this help me? Any thoughts on what I can do with that y? They both have a y, so we can factor it out. GCF. So if we take out that y, that leaves us with x minus 2. So it's y times x minus 2. The opposite of multiplying is dividing. So we can divide the x minus 2. Final notation, instead of y, we write f inverse of x. I also want domain and range. And let's do domain and range for both the original and the inverse, because we have two different functions here. So I use DNR for domain and range, and I do subscripts, either F or F inverse, to show me which one I'm talking about. In general, it's a lot easier to find a domain than it is to find a range. Okay, if we look back at the original function, the domain of the original function, we know that in a fraction, what cannot happen? The bottom can't be 0. So x can't be 1. So the domain of my original is everything except 1. Negative infinity to 1, union 1 to infinity. The domain of the original becomes what? Because the x's become the y's. So if I know the domain of my function, that is the same as the range of my inverse. Okay. Let's talk about the domain of the inverse. In my inverse, we have a fraction. We know that in a fraction, the denominator can't be 0, so x cannot be 2. So we write that as negative infinity to 2, union 2 to infinity. But when I'm looking at that, the domain of my inverse, so the x's of my inverse, what were those things to begin with? Those were my y's. That's the same as the range of my function. So if I ask you for those domains and ranges, it's a lot easier to find domain. So you look at the domain of the original and the domain of our inverse. Questions there? Let's try it. I'd really like to change this one. Can I change this problem? I want to give us another fraction one. I think we need more practice of those. Let's say I gave you x minus 1 over x. All right. So first step, instead of f of x, we write y. Then we switch our x's and y's. Now what would we do? So if we need to solve for y, if we multiply the y over xy equals y minus 1. Then what? Well, we need the y's on the same side. So I would probably subtract our y. We can't actually combine them, though. What can you do then, since we can't combine them? GCF, take out a y. That leaves us with x minus 1. So then we can divide by the x minus 1. So we have y equals, so at the end we change that to f inverse of x equals negative 1 for x minus 1. Alright, domains and ranges. Let's do that. The domain of the function is equal to what other thing? The range of the inverse. Okay, if I look at my original function, what can x not equal? to 0, union 0 to infinity. The range of the original is the domain of the inverse, so I can just look at my inverse. The denominator can't be 0, so x can't be 1. So that would be negative infinity to 1, union 1 to infinity. Questions? I have one last example on here. I'll go ahead and do it. I know the bell's going to ring in a minute for best writers. So tomorrow is just a work day. There are book problems. There are a couple where it tells you to graph the function and its inverse. You may use a graphing calculator on that. I probably wouldn't have you graph those by hand on the test. However, rational functions, which we just did on our last test, and that's quite involved, a lot of steps. So you can use a graphing calculator on those for the homework piece. But I wanted you to still see the graphs. However, last example of the day. We already said x squared was not 1 to 1, but I added the stipulation here. X is greater than or equal to 0. If I only plug in positives, 0 squared is 0, 1 squared is 1, 2 squared is 4. If I only look at positive x values, is this 1 to 1? Yes. So because I added this stipulation, we can't do it. So if I wanted to solve for, or first we have to change it to y equals, flip the x and y. If we want to solve for y, what do we have to do? Square root. Typically when you add square root, you do plus and minus, but we already know it's positive, so we don't need that. So y is just the square root of x. So final notation inverse is the square root of x. So sometimes you may have something that isn't 1 to 1, but if we're only looking at part of the domain, it might be. Any questions, sir? Just a thing on homework. What does EOE mean? So it's like 4, 8, 12, 16, if you need to write that out. I know that's got a few of you before. So you have a little bit of time now, and then the whole day